In this video, we're going to be taking a look at some non-homogeneous differential equations. So far, what we've looked at is the case when the right-hand side of a differential equation, a second-order differential equation, is zero. And we call these homogeneous. In the case where the right-hand side of the equation is some function, we call these non-homogeneous. And to be very general, we also will be looking at the case where not only is the right-hand side non-zero, but the coefficients are functions rather than real numbers. We won't be solving any of these at this point. We'll only be solving equations that have constant coefficients, but the right-hand side could be some non-zero function. Might be a number, might be a non-zero number, but it also might be a function. All right, what we're going to do now is we're going to state a few facts, and we're going to use those facts to build up to how to go about finding solutions to a non-homogeneous second-order linear differential equation. The first fact that I'm going to state is that if you have two solutions, y1 and y2, these are solutions to this non-homogeneous differential equation, then you can subtract those and you'll get a solution to the non-homogeneous differential equation. I think I'll call that one little y1 because I'm looking for a solution to this non-homogeneous differential equation. Sorry, this homogeneous differential equation. And I claim I can get that by subtracting two solutions, if I know what they are, to, actually, even if I don't know what they are, to this non-homogeneous differential equation. And here's how that works. Keep in mind as I do this, that this y1 and y2, big Y1 and big Y2, are solutions to this differential equation. So if I plug big Y1 in here, and here, here, and its derivative here, and its second derivative here, I'm going to get this function g. If I plug big Y2 in here, and its derivatives here and here, I'll also get g of t. So subtracting them, my claim is that by subtracting the two solutions to this differential equation, I'm going to end up with zero. And that makes it a solution to the difference, makes it a solution to this differential equation. So let's take a look at what happens when we do that. I know y1. Let me rewrite this first in my inimitable abbreviated way. Y1 is big Y1 minus big Y2. Y1 prime is, well, I'm going to take the derivative of a sum here, right, which is just the sum of the derivative. So I have y1 prime minus y2 prime, and y double prime is going to be the same, or be achieved the same way. So I have a double prime minus double prime. Y1 and Y2, big Y1 and big Y2 are different solutions to this non-homogeneous differential equation. And now that I know y1 and y2, or now that I know the first and second derivatives of my proposed solution, I'm going to plug them in here and see what I get. So let's do that. I have y double prime, where I'm going to use for the y double prime, I'm going to use this version of y double prime, which is this difference here. So I get y1 double prime minus y2 double prime. That's my y double prime. And to that, I'm going to add y prime. Well, y prime, I said, looked like this, y1 prime, big Y1 prime, minus big Y2 prime. And then I'll add b times y, which is y1 minus y2. Now, I'm not plugging these into this equation per se. I'm plugging these things here into the left-hand side of the equation, because what I want to find out is what happens when I do that, right? Keep in mind, these are y1 and y2 are known solutions. They're known to be solutions. We may not know what they are, what those expressions are, but we know that they are solutions to this equation. So a little distribution gets me y1 double prime minus y2 double prime plus a y1 prime minus a y2 prime plus b y1 minus b y2. Now notice that I have y1 things and y2 things, and all my y1 things are positive, and all my y2 things are negative. So let's rearrange these a little bit. I have y1 double prime plus a y1 prime plus b y1. I'll put that in parentheses. And from that, I'm going to subtract, and I'm also going to undistribute the negative as I go here. Y2 double prime plus a y2 prime plus a y2. And we know what this is because y1 is a solution, big Y1 is a solution to this differential equation. This whole thing here has to be equal to g of t. So that's g of t right there. And this is the same thing again for a different solution. It's y double prime plus ay prime plus ay. That's the same thing as I have on the left-hand side here for a different solution to this equation. So that thing there must also equal g of t. And from that, I get 0. Therefore, this particular combination, let me use a highlighter here, this combination of y1 and y2 is a solution not to this equation, but to this equation, because when I use it as to substitute in to the left-hand side here, what I get is 0, right? So if I were to plug y1 minus y2 into here, into this equation now, I'd get a true statement. I'd get 0 equals 0. So that means that this thing right here is a solution to the homogeneous version of this equation. This version of the equation is called the corresponding homogeneous equation to this non-homogeneous equation. So this is the corresponding equation. And if we know two solutions to the non-homogeneous equation, the difference of those two equations is a solution to this homogeneous differential equation. Well, that's pretty powerful because I know how to solve these by and large, right? I know that if I have one solution, then I can often find a second solution, depending on what A and B are, depending on what the characteristic equation is. I can find a second solution to this differential equation, and when I can do that, I can write all the solutions to this differential equation by using a combination of those. So this is a pretty powerful way to start finding solutions to the non-homogeneous equation. As it happens, it's even more powerful than this, because if you now take a look at this differential equation, remember we're not going to be solving these just yet, but I can apply what I've learned here to a differential equation with non-constant coefficients. And I can do that simply by saying, well, what if A is a function instead of just a number? And what if B is a function instead of just a number? Well, all I have to do to change this, this is essentially a proof of a theorem. I'll state the theorem in a minute. We've kind of already done that, but I'll come back to it in a second, is to change the A and the B in the function, in the equation or in the expression, to P and Q. I mean, I guess I could say A is a function of T and B is a function of T, but conventionally we don't use that notation. We use P and Q for our functions. So I'm just erasing all my A's and B's, and I'm going to replace them with P's and Q's, right? I have y double prime plus P of T times y prime plus Q of T times y. That gives me Py1 and Py2 and Qy1 and Qy2, and there's a P there and a Q there, P there and a Q there. I think I did that right. Yes. But I still end up with y double prime plus Py prime plus Qy, and that is Py double prime plus Py plus Q. I'll start over. Y double prime plus Py prime plus Qy. So that's still going to be equal to g of t. This one is still going to be equal to g of t, and I'm still going to get 0. So this thing that we did here applies even to non-homogeneous functions or non-homogeneous equations with non-constant coefficients. That's pretty powerful stuff. All right, so I'm going to state the theorem now just so we have it. If y1 and y2 are two solutions of a non-homogeneous differential equation, then the difference between those two solutions is a solution to the corresponding homogeneous differential equation. This is our theorem. In your textbook, it's numbered Theorem 3.5.1. That's kind of irrelevant. It just helps you find it in the book if you're looking for it at a point in time. That's our theorem, and it actually goes on. It's even more powerful than this. It also says if we have two solutions to the homogeneous differential equation, then I can write this big Y1 minus big Y2. I can write that as the general form, essentially, of the homogeneous equation. So I get C1 Y1 of t plus C2 Y2 of t. Almost ran out of room there. In other words, if I find y1 and big Y2 and take their difference, not only am I finding a solution to the homogeneous equation, I'm finding all solutions to the homogeneous equation. Now I'm finding all solutions to this version, right? Not to this version. But so far what I've got is the corresponding homogeneous equation. Once I have two solutions to the non-homogeneous equation, I also have all solutions, right, to the homogeneous equation. That's pretty powerful stuff. These are part 1 and part 2 of the same theorem. And we can take this even one step further. I'm going to rewrite this expression over here, this equation. Big Y1 minus big Y2 is equal to C1 Y1 plus C2 Y2 Y2. And I'm going to say, let's assume that Y2 is a particular solution, right? It's a very specific, known, exact, particular solution. So that means we're going to call it Y, just Y, because it's a known entity, right? That means I can replace Y2 with just Y in here. And then let's also make an assumption about Y1, and that is that Y1 is, it's one of two known solutions here, but it could be some other known solution, or it could be some unknown solution. But when we demonstrated this theorem before we actually wrote it out, we said that Y1 and Y2, big Y1 and big Y2, were known solutions of this non-homogeneous differential equation, but we don't actually have to know them, right? We're able to show that the difference of these two solutions, whether we know what they are or not, is guaranteed to equal 0, and therefore this difference is some y1 is a solution to the homogeneous equation. But we didn't know what y1 and y2 were. We just said they were some solution. So I'm just going to keep y1, y1. But then I'm going to add y to both sides of this equation. And that's going to give me y1 equals c1y1 plus c2y2, c2y2 of t, plus big Y of t, where y, with no subscript on it, is a particular known solution to the non-homogeneous equation, and y1 is any other known or unknown solution to the homogeneous equation. What this means is that this form right here is what we would call the general solution to a second order non-homogeneous linear differential equation. This y1 here in your textbook is replaced, and other textbooks use slightly different notation. They use the Greek letter theta there, or phi rather. So I'm going to erase y1, which is just our name for a random arbitrary solution. And I'm going to replace it with phi of t, just so that we have some consistency in notation with the textbook. An arbitrary solution phi of this differential equation will take this form. And the form is very interesting because it's the form, I'll use a different color highlighter. It's the form of the general equation of a homogeneous second order linear differential equation with a particular solution to a non-homogeneous version of the same problem tacked on at the end. So this is what we call the general form of a solution to a second order linear non-homogeneous differential equation. And actually, I'm pointing at this one, but I should be pointing at this one. This general form here is a solution to general solution to a differential equation, even when the coefficients are non-constant functions. So that's the theory behind. Oh, actually, I should point out that this is another theorem. We have the general solution of a non-homogeneous equation, y double prime plus p of t y prime plus q of t y equals g of t, can be written in the form phi of t, which is our general solution, right? That's what we're saying here. So the general solution can be written as phi of t equals c1 y1 plus c2 y2, which is the general form of an equation of the corresponding homogeneous equation, plus some known solution to the non-homogeneous form, the non-homogeneous equation. And then the rest of it just defines what those things are. y1, y2 they form a fundamental set of solutions. So that's this piece right here. I'm going to double highlight this. This piece right here is the general form of the homogeneous equation that corresponds to the non-homogeneous equation. In other words, it's the one where if you change this g of t to a 0, you get the same left-hand side, but the right-hand side becomes 0. Then this equation is the corresponding homogeneous equation that goes with this one, right? That's what we mean when we say the corresponding equation. It's the same stuff on the left-hand side. So this right here is the solution, the general solution for the corresponding homogeneous equation to the one that we're working with. So y1 and y2 form a fundamental set of solutions. So this linear combination here is the entirety of all the solutions to the homogeneous version. And then you just tack on this y of t. y1 and y2 are the fundamental set. I had to leave some stuff off here because I ran out of room. The rest of the definitions, if you were that C1 and C2 were just constants, and Y is any solution of the non-homogeneous equation, this thing right here. So Y is big Y is some solution to this, and as long as you know one solution to this, and you have a fundamental set of solutions to the corresponding homogeneous version, then you can write the general solution in this way. So I've kind of said that round and about several different ways there. Anyway, so that's another theorem. And with that, I think we're done with our analytical stuff, with our theory, and I think it's time to look at an example. Okay, let's say you're asked to find a particular solution to this non-homogeneous second-order linear differential equation. Recall that solutions of non-homogeneous equations will take this form: C1 y1 plus C2 y2, where y1 and y2 form a fundamental set of the corresponding homogeneous equation, plus some solution to the non-homogeneous equation. Well, that implies that we need to know what some of the solutions to what a fundamental set of solutions to the non-homogeneous form are. So why don't we start with that? Let's find solutions to y double prime minus 4y prime minus 12y equals 0. We can write the characteristic equation. This, I believe this will factor. Will this factor? Yes, 2 and 6. And we're going to need one to be positive and one to be negative. And so since it's minus 4, we need to make that one negative. So we have r equals negative 2 and r equals 6. So y1 is e to the negative 2r, negative 2t. And y2 equals e to the 6t. Well, there's my y1 and y2. So I'm going to have at least this much, c1 e to the negative 2t plus c2 e to the 6t plus some other function of t. Now, there are those who would argue that you don't really need to do this at this stage, because if you look at this thing right here, you're going to have a function that's a solution. You're going to take its derivative. You're going to take its derivative again. You're going to add up some combination of those things. And when all is said and done, you're going to have a function of e to the rt, right? E to some power of t, e to some power including t. And so it should be pretty obvious that these things are all going to have e to the t in them in some form or another. But we are going to need this information eventually anyway. So why not take the step here of finding out what y1 and y2 are, so that we can at least take a step towards finding out what our general solution is. All right, so now we have that, and we've also already discussed the fact that probably our solution is going to take the form of something that looks like the right-hand side of my equation. So why don't we take an educated guess? I'm going to say that y of t, and I'm going to call it y sub p of t because y, I don't know, p for particular. I'm going to say that it looks like my answer over there, but it may not have the same coefficient. So I'm going to say a is my coefficient. So I'm proposing that this is a potential solution, and if it is, then I need to be able to plug this y in, which is this expression right here, in place of y. I'm going to need something to replace y prime and something to replace y double prime with, so we're going to need to take the derivative twice of y of p. This is going to give me 5a e to the 5t, and yp double prime is 25a e to the 5t. And then I'll take these derivatives, plug them into my equation, and notice that I've still got an a in here. I've got some unknown value in here. That's the piece that I'm going to have to figure out. So I'm going to take each of these, plug it into here, and see what happens. And I'm going to do that off to the side because I can't do it below. I've run out of room again. I'll be rewriting y double prime minus 4y prime minus 12y equals 3 e to the 5t, with what I know y double prime to be, if my answer turns out to be correct, it's 25a e to the 5t. And then I take from that 4 times y prime, and y prime is 5 a times e to the 5t, and subtract from that 12 times just y, and y I'm proposing is a times e to the 5t. And if this thing is to satisfy this, if this solution is to work, if it's to satisfy the equation, then that has to all be equal to 3 times e to the 5t. All right, let's do some distribution. I have 25a e to the 5t minus 20a e to the 5t minus 12a e to the 5t equals 3 e to the 5t, and that is 5 minus 12 is negative 7a e to the 5t. These are all the same kinds of things. They're all a e to the 5t's. I have 25 of them here, take 20 from here, and take 12 more, and I have negative 7. equals 3e to the 5t. Now I can divide both sides by e to the 5t and divide both sides by -7. And I'm left with a equals -3/7. So now I know what my particular solution is going to need to be. This y sub p, this particular solution, a e to the 5t, will satisfy this equation as long as a has the value -3/7. So this particular solution that I was asked to find is y sub p, the particular solution, equals -3/7 e to the 5t. And with that, we now have a way to write the general solution. We have phi of t equals c1. Let me see, I'm kind of lost in all my notes here. Let me see if I can find my, here we go. I had come this far, right? There's my general solution before I knew what y sub p was. C1 e to the -2t plus C2 e to the 6t plus y, but I now know that y is negative, so that's going to be -3/7 e to the 5t. Now, if you take the first and second derivative of this function and plug phi prime and phi double prime into the left-hand side of this equation, what you should get on the left-hand side is 3 times e to the 5t. That's the whole point. You have found a function that satisfies this differential equation. All right, not all functions have a right-hand side that looks like this. So what do we do in the case where the right-hand side is a sine or a cosine? Or what do we do in the case where the right-hand side is, say, a polynomial? Well, those are similar problems, except that instead of our guess looking like this, because it has to, because that's what our right-hand side is, our guess will look different. This time, I'd like to take the approach of trying to find a particular solution to this differential equation without first solving the corresponding homogeneous version. And there's a couple of reasons for that. One is that I know you know now how to find the solutions to a homogeneous second-order linear differential equation. And the other is time. Not to mention that, well, there's a third reason. Sometimes you're only asked for that particular solution and you don't need the whole thing. So we're going to start with that this time. And then at the end, I'll explore, how you could branch out, find those, find the solutions to the corresponding homogeneous equation, whether you find it now or find it at the end. If you find it, then find those solutions, then you can expand your answer and find the general solution to this differential equation. Right now, we're just looking for a particular solution. So we're going to use the same strategy as we did before. We're going to say that my particular solution, my proposed particular solution, y sub p, is equal to something of the same form as the right-hand side of my equation. And then if that is going to satisfy the equation, then I'm going to need to be able to test with y sub p prime and y sub p double prime. Y sub p is going to be not quite. Let's see, the derivative of sine is cosine. But because of the chain rule, I'm going to have a 3 in front. And then the derivative of that is negative. The derivative of a cosine is a negative sine. And because of the chain rule, I'm going to have a 9 in front. Right, so 3 times the derivative of sine, 3 times the derivative of 3 cosine, and 3, I guess that's as far as I need to go. 3 times the derivative of 3 cosine is 9 sine, but it's negative. So those are my 3 functions, my original proposed solution, its first and second derivatives. So now we'll plug those in. Y double prime is negative 9a, the sine of 3t, minus 3 times y prime is 3a, the cosine of 3t. And then plus 2 times y, which I'm proposing is a, the sine of 3t. And that has to equal 3 times the sine of 3t. All right, so if I distribute, I've got a 9 here, so I have negative 9a, the sine of 3t, minus 9a, the cosine of 3t, plus 2a, the sine of 3t. Combining my sine terms, I have 2a sine of 3t minus 9a sine of 3t. I have minus 7a, the sine of 3t, minus 9a, the cosine of 3t, and that somehow still has to equal 3 times the sine of 3t. Okay, so where I am now is, in order for these two, the left-hand side here and the right-hand side to be equal, the coefficients of the sines must be the same. So I can make the statement that negative 7a has to equal 3. But it's also true that negative 9a has to equal 0, because there's no cosine on this side, and so its coefficient must be 0. If there's a cosine term on this side, then the corresponding cosine term that might be on this side would have a coefficient of 0. Solving both of these gives me a equals negative 3 over 7 and a equals 0. Now these are not the same. So what that tells us is that our initial guess, which was, we'll find it again, this thing right here, was incorrect. We made an educated guess, and it was a good, solid, the strategy worked perfectly well the last time, but it didn't work this time. So what are we to do? Do we just throw up our hands and say, oh, well, this one doesn't have a solution? No, not at all. In fact, the problem that cropped up here actually proposes something of a solution, right? We found out that the coefficients of sine would need to match, but the coefficients of the cosine term, they would also need to match, but they couldn't because there was no cosine term. So why don't we try a different y sub p? Why don't we try, since the work that we did here had both a sine and a cosine in it, let's try a times the sine of 3t plus b times the cosine of 3t. Yp's first derivative is going to be 3a cosine 3t plus minus 3b sine of 3t, and the second derivative will be negative 9a, the sine of 3t, minus 9b, the cosine of 3t. Plugging those in, I'm going to have to, let's see, I'm going to have to go down here. My y double prime is negative 9a sine of 3t minus 9b cosine 3t. And from that, I need to subtract 3 times y prime. And y prime is 3a cosine 3t minus 3b sine 3t. And to that, we're going to add 2 times y, and y is a, the sine of 3t, plus b, the cosine of 3t. And we'll distribute and reorganize. This is what I get when I distribute. I've distributed my 3 across here and my 2 across here. I get a 9, and then a 2 and a 2. And then I'm going to combine like terms. I'm going to combine all the terms that have cosine in them. So I'll collect all of those up. I guess I'll combine that with my, I'm going to collect all of my cosine terms, put them together and factor out the cosine, and then I'll do the same with sine. All right. So here is all of my cosines with the cosine factored out, and the same thing with the sine, just combine like terms. And this all has to equal 3 times the sine of 3t. So somehow, I'll get a different highlighter here. Somehow this has to equal 3, but this has to equal 0. So that's going to suggest a system of equations, or you could do this with a matrix, kind of depends on what you're comfortable with. I'm going to try to squeeze it in down here. I'm going to note, first of all, that my negative 9b minus 9a plus 2b, those could be further simplified, further combined. So I'm going to have negative 7b minus 9a, and that's the coefficient of cosine. That's the coefficient of cosine. If you go back to the original equation, there is no cosine term, so that has to equal 0. And then the coefficient of sine is negative 9a plus 2a, which is negative 7a, plus 9b. Did I get my sign wrong for the first one? Minus, where am I? Looking at the sines. No, looking at the cosines, I have negative 9b minus 9a, negative 9b minus 9a, and then plus 2b. So that sign is correct, that sign is correct, because that one's okay. And then looking at the coefficient of sine of negative 9a plus 9b plus 2a. Okay, so that sign is right as well. Okay, just double checking. That has to equal, this is the coefficient of sine, so that should be 3. And I have a system of 2 equations and 2 unknowns. I have several different ways. I mean, I might want to reorder these, right? Change this to a and b. Let's do that real quick. I would have negative 9a minus 7b equals 0, and negative 7a plus 9b equals 0. And you can use algebra to do that, or you can stick it in a calculator. I think I'm just going to do that. When I set up a matrix using the coefficients of a, b, and the constant over here, the constant coefficient, I get this matrix, and when I reduce it, I get this matrix. And that tells me that a equals, oh goodness, I think I'll just put it up here. A equals negative 21 over 130, and b equals 27 over 130. And so the particular solution that I'm looking for is, grab a highlighter here, this is the particular solution in which now I know a and b. So my answer here would be negative 21 over 130 times the sine of 3t plus 27 over 130 times the cosine of 3t. That is a particular solution. Now, sometimes that's the answer. Sometimes you are only asked for a particular solution, right? You use the information you have, you come up with this y of t. And sometimes you're asked to solve the differential equation or give the general solution. If you're asked to give the general solution, then we need to write that as phi of t equals c1y1 plus c2y2, forgot my 2, plus y sub p, where y sub p is this thing that we just found here, right? And in that case, as you can see, since I did not start by solving the characteristic equation, I would need to do that now. I don't know if I want to try to squeeze that in here or not. It's going to be r squared minus 3r plus 2 equals 0. That factors 1 and 2. So r equals 1, r equals 2. So my y1 is going to be e to the t. My y2 is going to be e to the 2t. And then, of course, I'll have this negative 21 over 130 sine of 3t plus 27 over 130 of cosine, oops, I got my 0, cosine of 3t. And I have c1 and c2 in front here. That would be my general solution. I have my general solution is c1 times y1 plus c2 times y2, where I've now found out exactly what y1 and y2 are, plus the particular solution from the non-homogeneous version of the problem. So it depends on what you're asked for. You have to be careful not to enter just this information, although that looks like a complete solution, doesn't it? It's long, it's got a lot of numbers and stuff in it. It looks like it could be the entire solution to this thing, but it's only part of it. It's only the big YP part of it. It's only the particular solution part of it. So when we say find a particular solution, we mean this piece. When we say find the general solution, we mean find the entire general solution, including the Y of P, which might be quite complex and long in its own right, plus this other combination of the two solutions from the homogeneous version. So be careful which question you're answering. Okay, here's another second order non-homogeneous differential equation. The left-hand side is the same as the left-hand side as the problem we did, not one screen before this one, but two screens before this one. So if I were to start by finding the solutions to the characteristic equation, I would learn that those two solutions were r equals -2 and r equals 6. So I have y1 equals e to the -2t, and y2 equals e to the 6t. And I'm going to go ahead and set that aside for the moment because I don't yet know whether I'm going to ask you for a particular solution or the general solution. So let's assume we don't know which one we're going to get. We don't have to do this right off the bat, but it doesn't hurt. As you can see, it takes very little space and relatively little time. But now what we have to do is find an equation, a particular solution, or a proposed particular solution that will satisfy this equation. And this equation has as its answer, if you will, as its right-hand side, a polynomial. So we're going to want our particular solution to take that form as well. But the highest degree here is 3, so we're going to say that our particular solution takes the form at cubed plus bt squared. I learned from the previous example that when there's no sign, there might still be a sign in the answer, or when there's no cosine, there might still be a cosine in the answer. In this case, there's no t squared in this expression here, but there could well be a t squared in my particular solution. And if there's not, then I'll just find out the coefficient is 0. So I might as well stick it in there. Plus c times t plus d. So my particular solution takes the same form as the right-hand side of my non-homogeneous equation, with, in this case, the exception that there is a t squared in my proposed solution, even though there's no t squared here. So if that's going to work for me, then it's going to need to satisfy that equation, and so I'm going to need to set up that equation, and so I'm going to need its first and second derivatives. That'll give me 3at squared plus 2bt plus c for my first derivative, and for my second derivative I have 6at plus 2b. Now, plug those in. Y double prime is 6at plus 2b minus 4 times y prime. Y prime is 3at squared plus 2bt plus c minus 12 times y, and y is at cubed plus bt squared plus ct plus d. That has to equal 2t cubed minus t plus 3. I'll go away and do my distribution and stuff like that off screen. I'll do it in a couple steps. I'll do the distribution first and then I'll come back. Okay, so this just came out of the parentheses, but then I distributed my -4 to get these values, and my -12, those were all 1, so that was easy. And that still has to equal 2t cubed minus t plus 3. Now I'm going to combine like terms. And I'm going to combine them by looking for all the t cubed terms and finding out what the combined coefficient there is, the t squared terms, the t terms, and the constant terms, because that's what I need to compare to the right-hand side here. All right, there is only one cubed term, so there it is out front. And there are two t squared terms, so they're there and there. And my t terms are here, here, and here. So that's, oops, it looks like I missed one. 6at minus 8bt, I missed that one, minus 12ct. So I just add my minus 8bt. And then the blue terms are my constant terms, 2b minus 4c minus 12d. Still has to equal 2t cubed minus t plus 3, though. Now I'll factor out those t cubes, t squareds, and so on. So I have a coefficient of t cubed, that's negative 12a, coefficient of t squared, that's negative 12a minus 12b, coefficient of t, which is 6a minus 12b, that should be, and no it wasn't, it was 12c after all. So the coefficient of t is 6a minus 12c minus 8b, and the coefficient of, well, the constant term, I guess, is 2b minus 4c plus 12d. So now I can look at this and say, well then, what that tells me is that negative 12a has to be equal to 2, because the coefficients of a cubed have to be equal. And the coefficients of t squared have to be equal. And the coefficients of t have to be equal. This one has a coefficient of 1. And the coefficients, well, the constants have to be equal. Well, there is no coefficient of, there is no t squared term on the right-hand side, but that still tells me something. It tells me that negative 12a minus 12b is equal to 0. And then I have 6a minus 12c minus 8b is equal to negative 1, and 2b minus 4c plus 12d equals 3. And again, frankly, I would put this in a matrix. I have negative 12a, no b's, no c's, and no d's, equals 2. I have negative 12a minus 12b, no c's and no d's, equals 0. 6a, no minus 8b, I was going to say no b's there, but they're out of order. Minus 12c, no d's, that equals negative 1. And no a's, but 2 b's, minus 4 c's, and 12 d's equals 3. If I reduce that matrix, I should get something that looks like this. And I'm going to call these A, B, C, and D, because that is what, once I know what those numbers are, that's what they will be. If you haven't done this on a calculator, that's all I would expect of you in this course for this. We're just using a matrix as a tool for solving what is clearly a system of equations. Right? This is a system of 4 equations and 4 unknowns. You can do it algebraically. There's certainly nothing wrong with doing it that way. In fact, here I can tell you that A is going to be negative 1/6, and once I know that, I can plug it in here, and then I can solve for B. Once I know A and B, I can plug those in here and solve for C. Once I know A, B, and C, I can plug the B and the C in here to find D. So you can do this algebraically, but if you know how to do it with your calculator, that's absolutely fine for this class. If we were doing, if this was a class in linear algebra, I would probably ask you to write out all the steps, but it's not. So I'm going to assume that you have a way of finding the solution to this system of equations, whatever that might be. Ultimately, what I'm looking for is these 4 numbers. And those numbers are negative 1/6 for A, 1/6 for B, negative 1/9 for C, and 5/27 for D. So now that I know what those numbers are, I can go back to, get the right pen here, I can go back to the proposed solution and fill in the blanks. So if I'm asked for a particular solution, that solution is going to be, where shall I put it? Y of t equals negative 1/6 t cubed plus 1/6 t squared minus 1/9 t plus 5/27. That is my particular solution. If, on the other hand, I'm asked for a general solution, that should be yp. It's going to be y of t, or if you prefer from the textbook, theta of t, your choice. Oftentimes in a computerized homework system like ours, it's that piece of the notation is given, and you're just asked for what's on the right-hand side. What's on the right-hand side is the linear combination of the two, of the fundamental set of solutions from the characteristic equation, the work with the characteristic equation that we did. C2, Y2, oops, that's supposed to be a T. Hang on. There, nope, wrong pencil. There we go. Plus negative 1/6 t cubed plus 1/6 t squared minus 1/9 t plus 5/27. So if you're asked for the particular solution, you give this answer. If you're asked for the general solution, you give this answer, which includes the particular solution, but also includes the linear combination of the fundamental set of solutions from the characteristic equation work. Whew, that's quite a lot to take in. There's a lot in this section, but I kind of like this section. It's fun. It's like working a jigsaw puzzle. All the pieces are there. You just have to figure out where they go.